Right, so this morning we are preparing for your little sort of assessment to see how you've got on with home learning, essentially. The assessment's going to be on forces, waves and magnets. We've done webinars on magnets and waves, so you can use any of those to revise from, but what we haven't done webinars on are forces, because that was self-directed learning, or it was learning maybe that you did in the classroom beforehand. So I thought that I would spend today just talking about some ideas and some concepts of forces to jog your memory mainly. So the first slide that we're looking at, some of you will recognise, okay, but it's a way to understand some key language that we will use to describe forces. We've got the phenomenon, which is just basically the thing that we want to sort of talk about, that we are describing. So we've got the word distance and displacement, scalar and vector, speed and velocity. And the way that we can understand these is by using a 400-meter racetrack that also, as we're aware from sports days, has 100-meter straight in it as well down here. Okay. So the first two words, we're working them in kind of like couples, really, distance and displacement. So the distance in 100 meters running race is 100 meters. Okay, so you go this distance, you go 100 meters. The distance in a 400-meter race is also 400 meters. It's what it is what it says, because you journey 400 meters. Okay, so the distance, I'm just going to see if I can write these in whilst I'm talking. So the distance is 100 and the distance here is 400. Now displacement is kind of like the route that you've not the route that you've gone, but the total from where you start to where you finish. So I start at 100 meters here and I finish 100 meters here. Okay, so I've actually been displaced the same amount as I have with my distance. So displacement is also a measurement. Now with my 400-meter race, I have gone all the way around the track once. I start here, but I also end here. Okay, so my displacement in my 400 meters is 0. I haven't actually gone anywhere. Okay, the other way that you can think about displacement is if we look at this picture here. Okay, this is a big distance. This is the Tour de France going up those hairpin bends up to Alpe d'Huez, and there's a big distance that these cyclists have to climb, but the displacement from top to bottom is far less. So the displacement is essentially like as the crow flies, okay, a direct line from top to bottom. The distance is the journey that they must take to get there. Then we've got the difference between scalar and vector. So let's have a think about this then. A scalar phenomenon, it fits on a scale. So for example, temperature. An earthquake can fit on a scale as well. A vector phenomenon, a vector event, also fits on a scale, but most importantly, it has direction. Okay, and that direction is in one direction. It's not constantly moving round. So if we look at the 100-meter race, it is scalar, but it's also vector as well. Okay, so yes and yes. It's scalar because it's 100 meters, I put it on a scale, and it's vector because it's going in one straight line. My 400 meters is scalar because it's 400 meters, it fits on a scale. But is it vector? No, because I'm going round in a circle. Okay, it's a circle. Okay. Then we've got speed and velocity. So if I run my 100 meters, I'm running at a speed because it's a distance in a given time. I can time myself. So I have got a speed when I run this. Do I have a velocity? Yes, because velocity is speed in a given direction. Okay, so yes, I do have a velocity. With my 400 meters, do I have a speed? Yes, it will probably be slower, much slower than a 100 meter. Okay, but Do I have velocity? No, it is constantly changing because my direction is changing. Okay, so the velocity is constantly changing as I go around these bends here. Okay, and then we've got speed from there. I haven't had any questions come up about that, so I'm hoping that we've all done a little bit of revision on that, and we're relatively happy with these concepts that I've gone through. The next bit is just to be really clear with ourselves about the two types of forces between contact and non-contact forces. These are the ones that are mentioned in the spec. Okay, so our contact forces are friction, air resistance, tension, and normal contact force, which is essentially the force that you are experiencing now sitting on your chair or wherever it is that you're sat. It's the force that essentially is pushing back up on you. Then we've got gravitational, electrostatic, and magnetic. And we've talked, haven't we, a lot on the magnet stuff about the forces that when electricity runs through a wire and how that force can, using that Fleming's left-hand rule there as well. Okay, so those are those ones there. To that, don't forget, oh yeah, sorry, I'm going to move on to this one next. Next, we've got about resultant forces. So a resultant force is essentially the answer that you get when you add multiple forces together or take multiple forces away from each other. So if we're looking at this little picture here of this car, we use the size of the arrow to determine the strength of the force, and those will be measurable amounts. You may be given that this arrow is worth sort of 5 centimeters or 10 centimeters, and something's equal and opposite, and so your force that is opposite that has to be the same value. So be very careful when you're putting your arrows in that they are proportional to the amount of force that there should be there. So we can see here that at this point we've got friction on each tyre. It's a small amount, but if we added all of those frictions together, it would be a bigger amount. The resultant force of friction would be all the mini ones from each tyre added together. But I also have another resistive force here, which is air resistance, and all of those are preventing the driving force from going forward. So I would add all of these together, and then I would take it away from my driving force, and that is how much it is moving in this direction, unless of course it's stationary or it's moving at a constant speed. If they're equal and opposite, it's probably moving at a constant speed. Here we've got very simple calculations, really simple, that if I'm saying if a rocket produces a thrust going forward of 2,000 but its weight itself is 1,000, what is the resultant force? So I've got 2,000 here, 1,000 here, it's going to go up by 1,000 newtons. Okay. Here we've got, putting it into a question, okay, a car with a weight of 5,000 newtons. So if its weight is 5,000, the force coming down from it, it's not going through the floor and it's not levitating. So if they're talking about something that's coming down, you also need to have the equal and opposite from that, okay, that goes up as well. And that would be that normal contact force of equal and opposite to 5,000 newtons. So it's got a driving force of 2,000 in one direction, and air resistance and friction totaling 800 in the opposite direction. So we've got in this plane, in this horizontal line here, we've got a 2,000 and an 800, so I take those away. So the overall resultant force of this one is 1,200 newtons moving right. Okay. Now some of you have asked about using vector diagrams and stuff like that. Now, obviously, when it comes to the exam, you will have a paper copy of your of your paper. Not now when you're going it. So you'll have, but we're not putting these into any of the questions today because and how can you? These have been done that on the if they need to do it and things. But we would suggest that you use for any force that is right angled, which most of the exam questions that I've seen, 99% is you've got something going and something going south. Okay, so you will always have what I've seen, sort of a right. So from my internet connection's unstable, hopefully that won't go. So what you would do from there is use Pythagoras. Okay, so some of you will go, oh yeah, okay, but let's just talk through that for those of you that aren't sort of like, oh yeah, of course. So if we've got, this is the directions of the forces that we've got, okay, and we've got this right angled triangle here. Now that's the same as saying that this is the same going this way. Okay, so I've got my forces here, okay, acting on each other, and it's the same. I could make a box out of it, which is what we did here, which is what we've been practicing in class, but this line is the same as going from here to here as well. So Pythagoras, don't forget, is a squared plus b squared equals c squared. Do not forget to use the square root to find c. Okay, and you will always be given A and B. Normally, the way that you're kind of like quite a.
Hi, Miss. I'm not sure if you can hear me, but I think the connection's gone a little bit. Hiya, Tam. I'm just going to give Miss a second to see if she comes back in.
Simple one, but I can hear you. Can you not hear me, Miss?
I can hear you now. You went for a little bit.
Really, so I think because yeah, I've got multiple people in my house probably online at the moment.
You're back nice and clear now, Miss. So.
Okay, thank you. And where did I cut out from, Miss?
You talked about Pythagoras theorem, and I think the A plus bit, and then that's where it's
okay, cool. So I talked here about a squared plus b squared equals c squared. So it's actually more accurate to work it out mathematically than it is to draw the line, really. So you would always be given a value for a and b if you're being asked to determine the magnitude and the direction of the force. And so the only thing with using Pythagoras is don't forget to square root the c squared at the end to get the actual value for c in there. And then you're just going to, at this point here, obviously the force in this one, if it's going this way and this way, the force is going in this direction up through here. And so then you're just going to get out your protractor, and then you can just measure that angle or guesstimate that angle or whatever that you want. Some of you might work that out mathematically as well, okay, using your SOHCAHTOA. So you can work out the angle from there, but you can use your protractor to work out which angle that you're going to do. And the mark scheme is very clear that it will say you could have this angle or you could have this angle from whichever line that it is. Sometimes they'll go all the way round, okay, because it will be that angle. If it's a you know, north, south, east and west, then you're going through there through 360, okay, to get to whatever angle that it is. But as I say, on this exam paper, because I've cut it into a Google form, there will be no, you would either have to explain how you would do it, or you would, I would have already pre-populated some lines for you, and then you would have to sort of like work them out from the information that has been given. And Pythagoras is the sort of gold standard, if you like, as to how to do that. Any questions about that, Miss, that have come through, or have you just answered them?
Nothing coming through, Miss. I'm just sitting here
waiting. That's all good. People have obviously done lots and lots of revision. So the next slide that we've got is about weight and gravity. Now this is a really useful equation, actually. Weight equals mass times gravitational field strength. Okay, and you're often given a mass of something, the field strength, and they're asked to work out the force that's acting on it, because weight is a force in newtons. So the way that we work this out, and let's just talk about this actually before we go any further. My mass is in kilograms, Okay, so in physics I would always convert to kilograms, and my mass is the amount of atoms essentially that make me up. And then my weight is the force of gravity that is pushing down on my atoms. So I'm going to weigh more on Earth than I am on the moon, okay, because there is less gravitational field strength. We need to be clear about that in our minds. What do we use to measure weight? We use a Newton meter to measure weight. Okay, we use weighing scales to measure, sorry, balances in science. Actually, it's a balance in science to measure mass, but we use a Newton meter to measure weight. And you should recognise these at various points. Okay, this one here's got a 0 error. All right, and so every time you did this, you would have to take that value off anything that you measured to make it correct. It's incorrect, it's got 0 error on this piece of equipment. So that's how we measure it. Then we've got this little slide. I think, have I gone again? No, I'm here. This mathematical symbol is directly proportional. Okay, so mass and weight are directly proportional to each other. I'm just working through some stuff. The centre of mass, let's look at this actually. So the centre of mass is a single point at which weight is centred. Okay, so the reason that the flamingo can stand on one rather spindly leg for so long is that it is perfectly balanced to have its weight in the centre that is directly above where that leg comes in. We've got these little toys that are balancing, and here's some pictures of people that have got obviously showing their centre of mass. We did an experiment, you would have done an experiment that looks a bit like this, where you found the centre of mass of an irregular object, and you had like a retort stand and a sort of an irregular shape, and essentially if you hang this shape by 2 points, 2 separate points, which are sort of here, running through this shape here, and then rotate it to hang through here, the point where they cross over is the center of mass of any object. So you just suspend something up from one end, you work out where it falls down, the line that it falls down, then you hold it the other way and you suspend it coming down there, and then when you cross them over, when you draw those lines together, you find the center of mass. And the piece of equipment that you use to do it is called a plumb line, and that's what builders and things will still use to find like a straight line with your hanging wallpaper or something like that, to make sure that it hangs straight down. We've got a load of triple stuff on these slides, which I won't go through. There's some pressure. Oh, and then we've got some stuff on speed was the next thing that we did. And really, I mean, it's the equation that you should know just intrinsically. Speed equals distance over time. The unit distance is in meters, time seconds. Really not uncommon to have to convert, okay? So if they're giving it in minutes, always convert it to seconds. And the unit of speed is meters per second. This is a distance time graph, okay? At this point here, my speed is increasing, so I'm moving at this point here. Here, I've not gone anywhere, I'm stationary at this point, okay? And then it's moving off again here. So if I wanted to work out the speed, it's rise over run. Okay, it's the distance that I've travelled divided by the time. So that's how I work out my speed here using that. Then we went on and talked about velocity, and we know that velocity is speed in a given direction, okay, and this had an equation to it. An acceleration equation is the change in velocity over time. That's what this means here. This little triangle means a change in velocity over time. And actually, if we think about this in terms of our graph, it makes real sense to us. This is a velocity time graph. Looks really similar, so just be really careful that you're noting what's on the left hand side. If it's speed, it means something very different at this point, okay? So here I've got uniform acceleration, okay, because it's a straight line, so I'm just accelerating constantly, okay, uniform acceleration at this point here. At this point, I am traveling at a constant velocity. Okay, my speed has not changed and it is in a given direction. It's a constant velocity. Here, there's some more uniform acceleration. And then at this point here, I'm decelerating. Okay, I'm slowing down. Now, higher tier only, the distance that I've gone is the area underneath this graph. So this is a math skill. Where you would have to potentially divide your graph up into triangles. Okay, so if I wanted to find the area under here, I would take this and I could do half base times height, okay, or I could find this area and divide it by 2, whichever way that you have been taught to work out the area of the triangle. Here I've got here I've got a little triangle and I've got a big triangle here. So I'd add all of those together and that would be my distance that I have travelled. Very common in higher tier is a question on acceleration and velocity time graphs and stuff like that to work out not only the acceleration but also the distance that they've gone. Working out the acceleration.
Hi, Miss, you've gone again. Hello, year 10.
Acceleration. Sorry.
Still jumpy.
Can you hear me? Oh, it's just said it's coming up unstable.
Yeah, you're still jumpy.
Can you see my?
I can see your screen.
Okay, do you want to talk through just for a bit? I'm going to
Nope.
Hello.
Didn't get that, Miss.
Oh, can you take over just talking about velocity? I was just explaining how to work out acceleration here
Okay.
using changing velocity. I'm just going to kick my kids off the internet.
Oh, okay. Yeah. All right.
Okay. I will not be a minute. Okay.
Okay, year 10. Hi, you've got my voice. I don't know if I need to start video. Hang on. There you go. You got my face as well. Excuse if I look a mess. Wasn't planning to be on screen. So if you need to calculate acceleration on a velocity time graph, it's always use rise over run. So rise is obviously up and then run is this way. And this bit's nice and easy because the change in velocity is from 0 to 40. So it would be 40. And then from here, we've got 0 to 10. So 40 divided by 10 would then give you your acceleration on this bit. If you were going to be calculating acceleration on this bit over here that I've got my mouse on, I'm hoping you can see the mouse, by the way. If not, I've moved over from 20 to 30. If you are calculating from that part, I think Miss is back now, so I'm not sure she wants to take
I am, but we're still just trying to, I'm going to plug in, you keep going, Miss.
Oh, okay. So if you were calculating acceleration here, we've got a change in velocity from 40 to 60. So you can either look at it and just go, well, 40 to 60 is 20, or 60 minus 40 to get to 20, whatever works for you. So the rise there would be 20 because it's changing velocity. And then we would look at the time. Again, we've got 20 to 30 for the run. Again, I'm looking at it and I can see it's 10. So that would then come up as 20 divided by 10 to give you your acceleration on this bit. Okay, so it just changes it depending on where you're looking at on the actual graph. And Miss, I think I'm done on calculating.
Excellent, thanks. Sorry, I just yeah, my children were took the opportunity for me not being in the room by deciding to go online and play their games and stuff like that. I've just thrown them off. So what we've got here then is interpreting some, this is distance time graph, just to interpret it for you. At this point here, notice on a distance time graph that this is acceleration. Now, what you might have to do, okay, is to work out the sort of a certain point in time. Here, it's easy to work out the steady speed at this point, okay, because it's a straight line. But in some cases, we would have to draw a tangent to the line to find out a point at exactly where they're asking. So just to remind you, a tangent is that straight line that runs that runs essentially sort of like parallel with the angles either side to the curve that you're doing. And then when you've got a straight line for the point that you want, you do the rise over run with the to fill in the triangle to go through there. Okay, that's higher tier only, and then that would help, you know, that means you can work out the acceleration overall, because if you just take it to be sort of, oh, at this point I'm going to do rise over run here, it doesn't take into account this curve. So the clue will be firstly the number of marks that it's worth, but also if you've got a curved line, then it would indicate that actually at this point I should draw a tangent to be able to answer that question. Obviously, on this quiz that you're doing, you can't draw a tangent because you know, it's not a paper copy. But this is if it might be a describe how you would do it, for example. What have we got here? Oh, this is another example of a velocity time graph, again saying that, you know, higher tier only, distance traveled or total displacement traveled by an object, and we work out the area under from there, and we can work out the acceleration, again as Miss said, which is that change in velocity over time, the one that we need to recall. Then I think what we'll go on to, there is a rearranging equation that's given on the worksheet. I'm not going to go into that too much now, actually, but there is an equation where you've got your final velocity equals, this is the one that's given, and you might then have to use that to find a distance as well, using acceleration with that. But actually I'm going to skip that for the minute, which might tell you something about the exam. We've then got a little bit about terminal velocity. So an object reaches its terminal velocity when basically the forces acting on it are equal and opposite. So here, if something's just been dropped, they only have the force of gravity. We've only got weight that is pulling it down here. But over time, a resistive force will build up, air resistance will build up, collect underneath the object, which will basically slow that object. So acceleration is slowed. It's still accelerating because it's still going, you know, this is bigger than here, but at this point here, there is no longer any acceleration going on. Because the forces are equal and opposite. That's Newton's third law. We'll go through that again in a sec, okay? And at that point, an object has met its terminal velocity. Yeah, here are Newton's third law, Newton's laws here. So his first law was that if a resultant force acting on an object is zero, what will happen to the object? So remember right at the beginning, we talked about resultant forces, didn't we? Right at the beginning of this little webinar, we talked about the fact that we can take away forces from each other that are acting against each other, or we can add those forces together. Now, if all the forces acting on an object cancel each other out and they're zero, then that object is either stationary, it's not moving, or it's traveling at a constant velocity. Now, be careful here, because you can't, these two words are not interchangeable in an exam question. If the exam question, it's clear that the object is moving, okay, but the resultant force is zero, you cannot say that it's stationary. Okay, you have to say that it is moving at a constant velocity, or they usually accept a constant speed as well. Okay, but constant velocity is the best one. So some people I have seen in the questions that have been answered on this have said, oh yeah, the object's stationary, where they haven't quite read the question to realise that the question tells me that the object's moving. Okay, so just be careful on that. Now, this tendency to be stationary or at a constant velocity is called inertia. Okay, oh, sorry. Let's go back to, where was I here? Newton's second law is force equals mass times acceleration. And so force and acceleration are proportional. Okay, and the inertial mass is how difficult it is to change the velocity of an object. Okay, how much do I have to sort of put in to be able to change that movement of it? This comes with a required practical, which is trolleys moving sort of along a ramp, and we're measuring the speed of them. That goes through there, and we work out that if we change the force that is applied, i.e. we put more pulling down on the trolley, then for any given mass, then obviously the acceleration is going to go faster as well. Okay, and then obviously if I have the same force but the mass is increased, then the acceleration is going to be lower. It's just an understanding of F equals ma, and that required practical, which some of you will have done, or you might have done it as home learning and looked up at it from there. Okay, but that might be one to look back at. And Newton's third law is that at equilibrium, the forces acting on the object are said to be equal and opposite. So if the resultant force is 0, which means it's at equilibrium, the forces acting on it are equal and opposite. Okay, that works through there. Then we've got some stuff that we did on braking. Most importantly with braking, it was what is stopping distance, and stopping distance is the sum total of the thinking distance and the braking distance that we've got here. We can test reaction times by that ruler drop test that we did in biology, actually, and a typical reaction time is between 0.2 seconds and 0.9 seconds. That was just a bit of content that would have to be done. So you might be asked things that might affect thinking distance, which is your reaction time. So that's things like tiredness, drugs, alcohol, caffeine. You know, don't forget things can speed it up as well as slow it down. And then braking distance, things that affect that are things to do with the car, so the nature of the tyres or the brakes themselves, and the road conditions at the time. So that would, if it's an icy road, then obviously it takes longer to brake from that. We then looked at calculating a braking force, which is essentially using F equals ma, force equals mass times acceleration. But obviously it's the opposite, because if it's acceleration, we can also use it as a negative value for deceleration as well. Okay, so you would use whatever the mass that you're given. You'd be given these values, and you'd have to rearrange to work that out. Flow diagram here, to show how a car decelerates. So these questions, they're quite specific actually. We need to think about how we would go about answering them. And so essentially a braking force here is applied to the wheels and brakes that increases the work done by friction. So work done is energy. Okay, so I'm applying a force to the wheels and brakes that increases the work done by friction to reduce the kinetic energy here. Okay, now the overall outcome of this is that these will thermal energy will dissipate from these brakes, because the energy has to go somewhere. It's not if it's not being reduced, if it's being reduced here, it's got to increase somewhere else. That store of kinetic energy has gone down, another store has to increase, and most often it's the thermal energy store that increases there. There was a question that I gave about regenerative braking, where actually that is used to recharge the battery and things like that, but that would you can more usefully transfer this energy, but typically it's used to increase the temperature of the brakes, and that will then by reducing this kinetic energy, deceleration occurs. Any questions about that, Miss? Oh, hello, are you there?
No.
Okay, no questions. Sorry.
So I had to get to the mute button.
Make a cup of tea, miss. The work done is energy. Okay, so the unit of work done is joules, and work done is moving a force through a distance. Okay, so work done is force times distance. Oh, look, here's a mass. Ah, right. What have I got to do? Ah, yes, mass equals mass times gravitational field strength equals weight. Okay, so actually these little equations, they're quite often used together. Really useful, that equation, weight equals mass times gravitational field strength, to get a force. Okay, and here I can work out the amount of energy by saying work done equals force times distance. Okay, so these are interchange. You'd have to do that one equation and then the other. How would you know to do that? Often the marks given actually would be a good starting point. If it's worth more than like 1 or 2 marks, it's like, perhaps I need to do something else here. So don't just be mindful that this cannot be applied to the work done equation. I need to do something else first. And then we did a little bit, although I'm not sure how much the triple science students have done on this, on elasticity. You might well have done the practical. I really can't remember now. Okay, which is about the extension of a spring. If you haven't done it here, this time, you've probably done it previously, and you will certainly do it again. I did a little video on it yesterday when I was in school, which I'll put out through the classrooms as well. And we were just talking about how force applied to a spring, the extension of that spring is directly proportional. I'll talk through that just quickly now. Okay, and then I guess, we're very nearly out of time actually, that our time slots that we're allowed. So I'll just quickly talk through this, and then we'll do, if anybody's got any more questions. Okay, so Hooke's law is essentially, sorry, let me just find it here. When an elastic object, such as a spring, is stretched, the increased length is called its extension. The extension of an elastic object is directly proportional to the force applied to it until the elastic limit is reached. By that, I mean until the spring breaks, okay? And you've all done it. You've got a spring and then it doesn't go back nicely. It looks all twisted and mangled. So this here, this is a really important phrase. This graph is directly proportional. There is no other way to describe this relationship, and this is why. Here is the origin, 0, 0, and it is a straight line through the origin. Here, the elastic limit has been met because it is no longer directly proportional. This is the sign for directly proportional. We've used this before. Okay, so if we're going to work out how springy a spring is, how soft or hard it is to stretch a spring, we use something called Hooke's law. He came up to this where he said that F and E are directly proportional, and we work out something called K, which is the spring constant. Spring constant, how springy a spring is. Okay, is it a stiff spring or is it a soft spring? Here is an example of that. So F equals KE, that's one to learn. Here you'll notice I put this little question in because I've given it in 12 centimeters. Extension is measured in meters, so always make sure that you do your unit conversions. It's very much a higher tier requirement for that. Okay, so you would just rearrange your equation to work out K. And here's some more stuff that tells you a little bit about when we stretch the spring. Obviously, for a string to move, something elastic to move, forces need to be applied. That could either be a compressive force or a stretching force as well, or even something pushed in from the side. Keywords: elastic deformation means that the object can return to its original shape. So here, what's happening to these strings is that we've got this force that's going on this way, but it would always return back until they've become elastically deformed, and you would need to, or they snap and they break, and then you would need to get your new strings for your guitar. And here, the tennis ball no longer bounces very well, which is why at competitions they change them regularly, so you have the maximum amount of elasticity still in that structure. Here's an example of something that can stretch, but will always then become inelastically deformed because it doesn't spring back. And these are the plastic bags that will stretch and then eventually tear, but they don't go back into their original shape. Okay. We've talked through these. Yeah, these graphs are important to be able to understand. This means that this is a stiff spring, okay, because I need here a lot of force to extend this spring at this point, okay. This is a really soft spring because I don't need very much force to extend it a long way. If we're going to look at it in terms of values, my force applied is going to be exactly the same here, but my extension is not very much. A little bit more and loads, we can see that as a spring gets softer, the spring constant value goes down. Okay, the softer the spring, the lower the spring constant from it, and you can work that out from here, because force divided by extension is this gradient of the line, isn't it? It's rise over run. Okay, so you could work out the spring constant from any point in this graph because it is directly proportional. Okay. The last thing that I'll talk about today in this revision session, and by the way, I've literally just talked through almost 3 weeks worth of teaching. Okay, you would have done all of this in 3 weeks. So if you're keeping up with this, this is amazing. Okay, really very, very, very good indeed. So there is an equation that relates to the energy that is stored in a spring. We first encounter it in P1 under energy. You'll be pleased to know you don't need to learn it. It is given on the equation sheet that you get given to help you with this. And it's basically saying that the potential energy in the elastic is equal to half times the spring constant times the extension squared. Okay, so this is very similar, isn't it, to the kinetic energy equation in point of fact. Those of us that know the kinetic energy equation, it's half times mass times velocity squared. Okay, there's a similar sort of setup in that way. So half times k times extension squared. Now here's an example of a question that I found on this. When stretched in position A, whatever it is, the elastic rope stores 25,000 joules. The elastic rope behaves like a spring with a spring constant of 125 newtons per meter. Calculate the extension, use the physics equation sheet. So you would find this equation and then you would just populate all the bits that you know. This means squared, by the way, if you were wondering what this little thing here means. And actually when you're writing it, you could write it like this in the exam as well. Okay, so putting all of those things in, we work our way through. So 0.5 times 125. If I divide that, I have to make that the subject first, equals e squared. So then I can do that sum to get to 62.5. And then finally, the last thing I have to do is square root. So that is an example of working through those, okay, and how that might be. It is possible that in this question, if it's like a big chunky question, that you would have stuff of, first of all, earlier on to work out K. You would have to work out K using F equals KE, then you take K and you stick it into this equation. These questions would be worth at least 5 or 6 marks if you've got to use multiple equations. And I have tried to put a few in leading up to this, so you not necessarily for this exam, because this is something different, but in where you've done questions before, where you've had to use 2 equations. Okay, so if it's worth a lot, then you need to think outside the box, or what other equation, how do I get there to get that? Okay, so that's me having talked through the vast majority of stuff on forces, and we are out of time, I'm afraid. Miss, any questions that have been answered? Anything else that you wanted to add?
No questions have come in. Just a reminder to my group that if they want a Zoom tutorial, they can book one in on the classroom if there's anything they still need help with.
Cool. Okay.
No questions.
Yeah, and so that's this form will be pushed out today. Okay, you'll have until Sunday to get it done, or Monday to get them done. Okay, and then we'll get back the we'll get back the scores to you. They're the usual, that, you know, you'll have all the mark schemes and stuff when they come back through, so you can see how you've done on it. And then that's quite a good point for you to be able to revise from. I didn't do so well on this, this is what I've got to revise on. And that's really what I want to stress about these things that we're doing. It's all about how you can get better at answering exam questions, identifying the gaps that you have, you know, in preparation for next year. Nobody is judging your result this year. Okay, and anything that you do, I'm going to push out what the for the triples, I'm going to give you what values you've got to get to get to a pass mark. In, you know, I'll give you the grade boundaries before you even get started, and you'll see that actually, you know, if you're learning all of this at home, most of it, you know, has been taught at home, to, you know, to achieve you know, a few marks on it is going to be amazing. It will be, you will have done really, really well. Please always hold that with you when you're answering this. Okay. You've done this yourselves. This is you that have got this far. So well done, and well done for joining today. I can see we've had a few people on already. Miss, anything to add?
No, but other than you're all awesome, but you know, I think that anyway. So
cool. Okay then, right, well, I'm going to end and stop recording. Okay, and so let us know if you need anything.